Hi students. In this lecture, I am going to discuss previous year's IIT questions. Let us see first one. Two thin circular discs of mass 2 kg and radius 10 centimeter each are joined by a rigid massless rod of length 20 centimeter. The axis of the rod is along the perpendicular to the planes of the disc through their centers. This object is kept on a truck in such a way that the axis of the object is horizontal and perpendicular to the direction of motion of the truck. Its friction with the floor of the truck is large enough so that the object can roll on the truck without slipping. The x-axis as the direction of motion of the truck and z-axis as vertically upward. If the truck has an acceleration of 9 meter per second square, calculate the force of friction on each disc, the magnitude and direction of the frictional torque acting on each disc about the center of mass O of the object. Express the torque in the vector form in terms of unit vectors I cap, j cap, and k cap in the x, y, and z directions. Let's see the question carefully. So having there two circular discs, mass given, radius given, joined by rigid massless rod that length is 20 centimeter. Given axis of the rod is perpendicular to planes of disc through their centers. That we can see in diagram. This is now axis, okay? Normal to the plane of the disc through their center of masses, okay? This object is kept on a truck in such a way that axis of the object is horizontal and perpendicular to the direction of motion of the truck. So given here truck is moving along x-axis, right? It has acceleration 9 meter per second square. Given x-axis as direction of motion of truck. That means we can see in diagram this axis will be along y-axis, okay? Because direction of motion is x-axis and this will be now along y-axis, right? Let us focus how to start. Right. Let us see first of all. Focus one disk because on each disk friction will be same. So I'm focusing only one disk. This is now disk. Let us take this as x-axis. Okay. This as x-axis. And this is z. Now say ask for given data. It has acceleration along x-axis and that acceleration I am taking as a suffix t. Acceleration of truck, okay? That is given as 9 meter per second square along x-axis. Let us take frictional force at the contact that as along positive x. Let us take frictional force at the contact along positive x-axis. Frictional force. Since it is rolling without slipping, friction will be static. Okay, it is Fs. Now you can see because of this friction, torque will be anti-clockwise, right? About center of mass, because of friction, torque will be anti-clockwise. Now, since we are solving from ground frame, now this frictional force becomes net force along horizontal. Okay. So along x-axis, net force is frictional force. Right. Now see condition. Since no slipping for contact point, I can write net force is along x-axis. Therefore, ACM, ACM will be right side. Okay. And because of rotation R alpha, it is also right side. So first condition I can write here ACM plus R alpha should be equal to acceleration of the truck. So I hope you are getting this point. Frictional force is right side. This is now net force on the disk. That means acceleration of center of mass must be right side. So ACM. Because of this friction, torque is anti-clockwise. That means because of rotation for contact point, tangential acceleration is right side. So ACM plus R alpha should be equal to 80. Okay. Next. In the place of ACM, see what we can write? F frictional force upon mass of the disk, right? Plus R into, in the place of alpha, see what we can write? Alpha equal to, I am writing here, torque equation, Fs into R, that is a torque about center of mass due to friction, which is equal to I into alpha. I value mr square by 2 into alpha. Now simplify for alpha. R gets cancelled. Alpha equal to R, calculate directly R alpha. Okay. From here, R alpha equal to R alpha equal to 2Fs upon M. Substitute that here. Okay. 2Fs upon, and I have taken R here. So I'm placing R so that R cancel. That is equal to 8. Okay. Now simplify this. Fs by M, 2Fs by M, 3Fs by M, or M into 8. Okay. Then see what we get. 3Fs is equal to mass. See mass, how much given? It is for each disk mass is 2 kg. Acceleration is 9. Okay. So 3 here, 3 times. So Fs equal to 6 Newton. Okay. So just writing condition for no slipping. Okay, rolling without slipping. Right. Next. Focus now. In that, what else we have to calculate? The magnitude and direction of frictional torque acting on each disk about center of mass O. Right, see carefully. Let us make a diagram. This is one disk. This is one more disk. Okay. So we can take now x-axis now into the board. Okay. For this a plane board, it is normal into the board. And this is y-axis. X is into, and this is now z. Okay. Right. Now see where is the point O. Point O is now, this is midpoint of the rod. This is O. frictional force is acting at the contact, right? And we got frictional forces now along positive x-axis. Okay. So point of means position vector of the point of application of force, because a torque equal to tau bar equal to r bar cross f bar. So we want position vector of the point of application of force. Okay. With respect to this, see for this one, torque equal to, or I can say torque on this left one. This is the left one. This is the right one. On the left disc, okay. Torque on the left disc, that is equal to R bar. So R bar means this total length given 20 centimeter. This is now 10, means 0.1. So 0.21 J cap from here down, okay. That means minus 0.1 K cap. That is now position vector of the point of application of force. And force is now 6 I cap along positive x-axis. So 6 I cap. Okay. Now see 0.1 and 6. Take 0.6 outside. Remaining is now J cap cross I cap. That is minus K cap, right? J cap cross I cap is minus K cap. Next, minus K cap cross I cap. That is J cap. This is now torque of frictional force about this point 2. Okay. Now coming to on the right one. On the right one. See, only change is now. This is minus. Okay. Because we have taken left as y-axis. Okay. Right will be minus. So minus 0.1 J cap. And this remains the same. No change in that. Minus 0.1 K cap. Force as usual 6 I cap. So only changes now. This first part will be positive, right? So I'm taking 0.6 outside. J cap cross I cap. That is minus K cap. Minus of minus plus. That is K cap. Minus K cap cross I cap. That is J cap. Okay. So main thing, writing the condition for no slipping. And remain just by using definition of torque, R bar cross F bar. Okay. Let us see for next problem. Let's see the question given. A homogeneous rod AB of length 1.8 meter and mass m is pivoted at the center O in such a way that it can rotate freely in the vertical plane as shown. Given it can rotate freely in the vertical plane. That means the axis is now horizontal. The rod is initially in the horizontal position. An insect S of the same mass falls vertically with the speed V on the point C, midway between the points O and B. See diagram. This is rod AB. O is now midpoint. An insect falls at the midpoint of OB. Okay, with a velocity V. Immediately after falling, the insect moves towards the end B such that the rod rotates with a constant angular velocity omega. Condition given that it rotates with constant angular velocity. Determine the angular velocity omega in terms of V and L. If the insect reaches the end B when the rod has turned through an angle of 90 degree determine V. Okay. So asked for 8 marks in 1992. Let us see how to start. Right. So first focus that given data. Homogeneous rod AB length 1.8. Initially rod was horizontal. Insect falling at the midpoint of half part. Okay. So you can see diagram here. A, O, B. This is A, this is O, and this is A. Insect fall now at the midpoint of OB. Right. Now see what happens. Let us take now after some time. Or we can say at one point of time. Let us take rod is making an angle theta with initial position. Suppose rod is making an angle theta with initial position. This is now position of the rod at one instant. Okay. Let us say insect is now somewhere here. Insect is now somewhere here. Suppose its distance is x from the axis of rotation. So take distance is x from this axis of rotation because condition given that. So immediately after falling, insect moves towards the end B. It moves like this. Okay. Right. Now see what we can say here. Towards B such that rod rotates with a constant angular velocity omega. Right. So in this, what I can do is we can take now conservation of angular momentum. Okay. To find omega in terms of V. And before that, first focus how to get value of omega. Okay. To find omega, so here what I'm doing is about this axis of rotation, focus now torque equation. About this. About this torque means it is only because of weight of the insect. Weight of the insect. That is now mg downwards. So because of weight of the insect, torque about this axis of rotation. See how much? This is a point O. So torque about that point O is equal to mg into this is now x. We want now this length, okay? That is x cos theta. So mg into x cos theta. This is now net torque, okay? Net torque equal to see here we should not write I into alpha. Okay. So we can write I into alpha only if I is a constant. Okay. So here I is not a constant. For this we have to write dl by dt. So net torque equal to dl bar by dt. Okay. Next. So in the place of L, what we can write? This is mg into x cos theta. That is equal to L equal to I omega. Condition given that omega is a constant. So I'm taking omega outside. Remaining is now di by dt. So d by dt of, see what is I value? Moment of inertia, right? About point O. That is now mx square. Because distance how much? X from axis of rotation. Right? Now simplify this. Mass is a constant. I can cancel directly here only. Next. Next, what else? When I'm taking derivative here, 2x dx by dt. right? It is 2x dx by dt. I am writing here gx cos theta, that is equal to omega 2x dx by dt. Okay. Now simplify this. X gets cancelled. Omega the constant. Omega constant and 2 constant. I am taking here g by 2 omega in the place of theta. I can write it as cos omega t, right? Since omega constant, theta equal to omega t. Integration of this omega t dt. That is equal to left side. See what is left? It is only, sorry, right side. It is integration of dx. Okay. Now we have to find omega value. See, once determine the angular velocity omega in terms of v and l. Okay. So I'm writing here 0 to 0 to x value, right? X value we are taking from where? X we have taken from point O. From point O to from point B. Distance equal to L by 2, right? Distance L by 2. So 0 to L by 2. Okay. Wait. Why we are taking 0 to? We have take insect falling midpoint of O and B, right? So starting from X L by 4. So let me correct it. It is L by 4 to L by 2. Okay. So when it is L by 4, what was the angle? 0, right? Because rod was horizontal, means theta equal to 0. L by 4, it is 0. So x equal to L by 4 to x equal to L by 2. 0. And this is now, see how much? So when it reaches the point B, it turns by angle 90, right? See question carefully. Insect reaches the end B when the rod has turned through an angle of 90. Okay, right. Now simplify this. G by 2 omega integration of cos omega t, that is sin omega t upon omega. Take limits 0 to 90, that is equal to L by 2 minus L by 4, that is L by 4. Okay. So 1, 2 gets cancelled here. And this becomes 1, right? Because sine t value substitute here, means in the place of, we can take directly in the place of omega t. Okay. Omega t value directly pi by 2. Sine 91. Next one 0. So it is now g by omega square. G by omega square is equal to L by 2. That means omega value how much? Root of 2g by L. That is a value of omega. And if you take values in that, see how much we get. Root of 2, g value 10, L value, see once L value, right, it is 1.8. It is 1.8. See how much we get? 0.9. This is now, so that comes out to be 100 by 100 by, it is 9, right? Means 10 by 3 radian per second. Okay, right. So we got the value of omega. Now we have to get the value of v. See what we're asking here? Determine angular velocity in terms of v and l. Okay, and also we have to find v value, right? So for that here, what I'm doing is using conservation of angular momentum about It is just before, okay? Just before colliding, just after colliding. I am repeating. We are taking conservation of angular momentum just before collision, just after collision. So in that case, what happens? Even though torque is there due to weight of the insect, I am writing here net torque equal to dl bar by dt. Net torque is due to gravitational force of the insect. But we are taking just before, just after. So dt value very small. So this torque into dt becomes very small. So change will be almost zero. Okay. That's why we are writing here conservation of angular momentum. So I'm writing here it is now just before m into v into L by 4. Distance from axis of rotation is L by 4. That is equal to I into omega, right? What is I value? See, I value for the rod ml square by 12, right? Next, for the insect m into L by 4 whole square means L square by 16. Okay, this value how much say? 16 plus 12, 28. 28 upon 12 into 16 ml square. Okay, see the calculation part. 4 7 times and here 4 times. Substitute that here and here you can substitute omega, right? 10 by 3. Okay, so m v L by 4 is equal to 7 by 4 m L square, that is I value, omega value that we can substitute 10 by 3. Okay, first make calculation. M gets cancelled, 1 L gets cancelled. Okay, next wait. You're having your 4 and 12, 12 is there, 12, 4 gets cancelled. That implies V equal to 7 by 12 L omega, right? L value, it is 1.8. Omega value, how much we got? 10 by 3. Cross check once. Now 10 into 1.8, 18. Okay, 18. 18. This is 3 12 36. 18 36 means 2 times. 7 by 2. That is meter per second. Okay. So here what we have taken? Conservation of angular momentum just before sticking or just before collision, just after collision. Okay. Right.